Hello everyone, welcome back to the channel. In this video lecture, we shall solve this problem longest common subsequence. So in the problem statement, we given two strings x and y, and we have to return the length of their longest common subsequence. If there is no such common subsequence, then we return 0. So what is a subsequence? A subsequence basically is a set of characters which are taken from the parent string in the same order in which they appear in the parent string. For instance, from this string A, B, C, D, E, we take characters A, C, and E in the same order A, C, E. So that's why it is a subsequence. So A, C, A, D, A, C, E, A, C, D, E all are subsequences. While let's say if we take C, A, then this is not a subsequence because although C, A appears in the string, but the order is reversed. C appears before A, while in the parent string C appears after A. So that's why this is not a subsequence. Okay, so let's see the input format. We'll be given two strings x and y in two lines. The strings contain the lowercase English letters, and the output will be an integer number which represents the length of the longest common subsequence. So let's see an example. Before that, let's see the constraints of the problem. The length of the strings goes up to 1000, and the strings contains the lowercase English letters. So let's take an example. For instance, here in this set of strings A, B, C, D, E and A, C, E, the longest common subsequence has a length of 3, which is A, C and E. Okay, so that's why the answer is 3. We can see that there is no subsequence which can be greater than A, C, E, that is of length 3. Hence the answer is 3. Let's see an example. So there are two strings A and B. Okay, so these are the possible matching subsequences. So these are the subsequences which are present in both A and B. Out of all of them, this one has the largest length of 5. B, B, G, C, G, F. B, B, C, G, F. Hence the answer is 5. All other subsequences has length less than 5, hence they are discarded, and we take this as our answer. Okay, so let's see how we can solve this problem. First, we'll start with the brute force approach. In the very naive approach, what we can do is it's simple to think that we generate all subsequences of this string, and for each subsequence that we generate, we check whether that exists in the string B or not. Okay, that can be checked in linear time complexity. Okay, so for generating the subsequences, we require how many subsequences a string of length n has. So it will have 2 raised to the power n minus 1 subsequences. If we do not consider empty string as one of the subsequences, then these are the number of subsequences that a string of length n has. Okay, how? Let's take an example. A, B, C. The subsequences will be A, B, A, B of length 1, then C, we will have A, B, A, C, B, C and A, B, C. So you can see there are 7 subsequences and the length is 3, so 2 raised to the power 3 minus 1, it is 7. This is because to generate the subsequences from this parent string, let's say we start with empty string. Now at each character we will have two options. Either we take it into the string that we are building, or we do not take it into the string that we are building. So now after traversing first character, I will have two possible states or two possible ways to generate the final string. Then same goes here. I can take second character into the string to create a, b, or I just keep my a as it is and skip the character second. Same goes for this. So that's how finally I will have 7 strings here, 7 subsequences of the parent string a. Okay, so that's how I generate my subsequences from the given string a, and the time complexity is 2 raised to the power n, because the branching factor for each let's say for each function, for each node, we can say it is 2, and the height of this tree will go up to n, where n is the length of this string. So that's why the answer, the time complexity will be 2 raised to the power n for generating all the subsequences. And for checking whether that subsequence exists in string b or not, it will take big of m time complexity, where m is the length of the string b, so that will give me overall time complexity of this. So it is not possible to execute this approach on the constraints given in the problem. That is, the length of the strings goes up to 1000. So 2 raised to the power n will become 2 raised to the power 1000, which will give me TLE. So this is not executable. Okay, so that's why we have to think of an alternative approach to solve this problem. So let's see how we can solve this problem. So the idea is simple. Imagine we are traversing the strings from the last character. So imagine we are traversing the strings from the last character. Let's assume a hypothetical subsequence. Assume that this is the final subsequence that we will have. Now we start from the last characters of strings a and b and check if they match or not. They are matching. If the characters are matching, then I claim that this character will be the last character of the longest common subsequence that I am trying to generate. F is the last character of the LCS that I am trying to generate. Okay, then, and the length of whatever the length I will have for the entire longest common subsequence, it will decrease by 1. That means now I want to find the length of LCS for this set of strings, because I have found the last character of the subsequence. Okay, so let's say it returns me x, the longest common subsequence for this set of strings is x. Then the final answer will be x plus 1, because the last character is added here, and that's adding the value 1 here. Okay, so this is how we proceed. Now we move to next character, that is g. Okay, and you can see that g is also matching with this character is also matching with the second last character of string b. And now I say the second last character in my longest common substring is g. Now I want to find the longest common substring in this part of the string, namely a b c d b b a d c. Okay, so that will give me the longest common subsequence for the entire string, because let's say this part returns me x, and I already know that 2 characters have been matched, g and f, so the final answer will be x plus 2. Okay, now let's move to the previous character d and c. So they are not matching. Now if they are not matching, but I'm saying, okay, d is not matching with c, maybe d will match with some character which is present in this part of the string. Okay, so I find the LCS, I try to find my LCS in this set of string, namely a b b c d b b a d. I skipped the character c. Okay, so that's how I find my LCS. And other case can be with respect to string b. So in the previous case I skipped c and checked for this string and this string, while in this case I will skip D and I'll check for this string and this string. So now I want to find the LCS in this string. So I have two cases here, and whatever case returns me the maximum. Okay, let's say this case returns me X, while the previous case, which was to take the string to find the LCS in this set of string. Okay, so in this set of string, this was returning me Y. Okay, then I will return max of this X and Y to the calling function. Okay, so this will be returned, and in this result I will add 2 because I have GF already constructed. So this will be my final answer. So that's the idea. That's how I will solve this problem. Okay, so I hope you are getting where we are going. You may have got the intuition of a recursive solution for this problem, and let me show you how we build the solution. So I want you to imagine a function LCS a b I j. This function basically gives me the longest common subsequence of strings a from 0 to I minus 1 and b from 0 to j minus 1. Here I and j are the lengths of the strings a and b. Okay, initially they are the lengths of the strings. Okay, so initially I is m, here I pass n here, and here I am passing m, where n is the length of this string, m is the length of this string. Okay, so how will the body of this function look like? How this function will work? So we know that initially this function will be called at last index, because I want to find the LCS for the entire string. So I will call this function over the last index, which is 1 2 3 4 5 6 7. So 7th character of the string A, 7th character of the string B. Okay, because they are of same length. Of course the strings can be of different length as well. Okay, so this is not a general case. There can be set of strings which are of different length. Okay, now this function is called, I'll check if the 7th character of A matches with the 7th character of B, and the answer is yes, they are matching. So I will call this function for the previous prefix here for this set of strings here. So I will pass 6 and 6. Okay, and since I know that the last character has been matched, whatever result that this the LCS for this strings will return, let's say X, I will add 1 into it. So this is the function call for this set of strings, and I'm adding 1 here. Okay, then I match 6th character of A with the 6th character of B, so they are matching. G is matching with G. Again I repeat the procedure. LCS will be called for first 5 characters of A and then for first 5 characters of B. Now this character D is not matching with the character C, so I will call the LCS function over. Okay, I forgot to add 1 here. For LCS function for the first 4 characters of string A and 5 characters of string B, and LCS function for the first 5 characters of string A and first 4 characters of string B. Why? Because D is not matching with C, so what I am claiming, maybe I will find my LCS in this set of strings. Okay, in the first case. And in the second case, what I am saying, okay, D is not matching with C, C is not matching with D, maybe C will match in this part of the string, in this part of the string, and say if this returns me X and previous case returns me Y, then I have to take the max of these two. So max of these two will be the answer. Okay, so let's see how we can implement this function. How does the body of this function looks like? We can predict that there will be 2 cases. Let's say the first case will be for when the characters are matching, and the other case when the characters are not matching. Okay, and this is how the function will look like. This is the case when the characters are matching, so the ith character of A is matching with the jth character of B, string B, and in that case what I am doing, I am just calling the function by decrementing the indices by 1. So if I is here and j is here, since they are matching, we'll call the function for this prefix and this prefix. Okay, this is the first case, and I'm incrementing the result by 1 because the characters has been matched, and the subsequence ends at character I of A and character J of B, either of them, because they are same. Otherwise we call the function by skipping the one of the characters of either string A and or string B. So here I am skipping the character for string B, and here I am skipping the character for string A, and I will take maximum of the results returned by these functions. And this is the base case where I exhaust one of the strings. So if one of the strings is exhausted, and then the LCS for the empty string versus empty or a non-empty string is always of length 0. Okay, so this is the final function which we have here, and let's see how. Let's dry run this function over this sample input. We have A as of length 5 and B as of length 3, so that's where I'm calling my function LCS for A and B, and I see that the character number 5 of A and character number 3 of B are matching. Since they are matching, I'll call the function for a prefix of length 4 and prefix of length 2 for strings A and B, and I will add 1 to the result, which is returned by the longest common, which is returned by the LCS function for this set of strings. Okay, so that's what I am doing here. And now I see if the fourth character matches with the second character. No, it doesn't match. Then this case arises. I call the function for this set 3 2. Okay, and I call the function for this set, that is by skipping C here, for the set 3 2 and for set 4 1. Okay, and whatever like out of these two functions, the function let's say this function returns me x, this function returns me y, then I will return max of x and y to the calling function LCS4. Okay, so now for this function I know that character number 3 is matching with the character number 2. Okay, so you can see that character number 3C is matching with the character number 2. So that's why this case arises. I call the function for A, B and A here and increment the result by 1. Then I see that 2 is not matching with 1. So this case arises. So I call two functions here. Now here you can see the first character is matching with the first character. So LCS 1 1 will be 1 because the LCS for A and A is 1 because A is the only character which appears in both the strings. So this is returning me 1 here. So this will return 1 here in turn. So this is 1. 1 plus 1 2. So this will return okay, so notice that LCS 2 0 will return me 0 because the LCS for a string of length 2 versus a string of length 0 is 0. Okay, because we know that empty string versus non-empty string, the LCS is 0. So this will return me 0, this is returning me 1. So max of 0 and 1 is 1. So that's why I end up with 1 here. 1 plus 1 is 2. So this is returning me 2. So this will become 2. So this function will return 2 here. Okay, and here now let's see what is going on here. In this branch I called the function for prefix of length 4 versus for a prefix of length 1, and I see that this D is not matching with A. So this case arises. I call the function for this prefix and the same prefix of length 1 and the prefix of length 4 and with an empty string. So this and ends here, so this will simply return me 0, and this 3 1, so for A B C versus A, this will obviously return me 1 because we have, like, for A B C and A, the LCS is of length 1 because A is present in this string, so this is returning me 1. So 0 versus 1, the maximum of them is 1, so this function will return 1 here. Okay, so but I will compare 1 with 2, okay, and I will take max of them, max of these two. Okay, so this will return, so this will give me 2 here. I will end up with 2 here because 2 is greater than 1. So 1 plus 2 is 3, so I will return 3 to the calling function. Hence the longest common subsequence of string A and B is of length 3. Okay, so let's see the time complexity of this code. You can observe that at each character, I'm calling the function, like here at each node, the maximum number of functions that can be called are 2, so the branching factor is 2, and the height of this tree goes up to the length of the string or larger length of the strings. So let's say this has length n and this has length m, then the height can go up to max of n and m. Hence the time complexity will be exponential, that is max of n m, and this is huge because the length of the strings goes up to 1000, so the operations goes up to 2 raised to the power 1000, and this is huge. It will give me TLE. Okay, so we have to improve upon this solution, and for that, let's see if we can memoize this code. For that, we have to check if we have redundant function calls. There are two properties to check. The first one is optimal substructure, and the second one is repeating subproblems. So you can see that this function 20 is called here, 20 is called here, 20 is called here. So okay, so this should not be 3 and 1. So this should not be 20. It should be 2 1 and 3 1 and 20. Okay, so so this function is repeating, 20 is repeating here. Therefore we have to memoize this code. We can memoize this code so that we can reduce the time complexity. And let's see how we can memoize this. Observe that at each level there are two indices that are changing, I and j. Okay, so two variables are changing. Okay, therefore the DP state that we will have, it will have two variables. Fine. So that's why I'm using a matrix of dimensions n cross m, where n is the length of string A and m is the length of string B. So this represents the string A and the columns represents the string B. Okay, so what is the purpose? What is the purpose for doing this? It is just to store the results. So once the result for a particular set of values, for instance for this function LCS21 is computed, I do not have to compute the result for LCS21 again anywhere. I have memoized the result. I have stored this result for at this location 2 1 here, such that whenever LCS21 is called, I simply return the result which is present here and do not have to make the unnecessary computation which I am doing here. Fine. So that's the purpose of memoizing the code. So let's see the memoized implementation for this problem. So this is the memoized code. what I'm doing is, okay, before that I will initialize my array with -1. This is to check whether the result for a particular set of values is already computed or not. So if -1 is present here, what it says that, okay, the result for LCS 11 is not computed yet, so it is safe to call this function. Okay, so that's why we put -1 in the matrix, and this is the case covered here. So this is the base case. This is to check if the result for that particular set of values is memoized or not. If it is memoized, then we return the result right from here. Otherwise, we compare the characters that we are trying to match. If I character match with j character, then we call the function for the strings from for I-1 and j-1, and increment our result by 1 and store it for that particular set of indices. Otherwise, we cover here the two cases that we discussed earlier, and that's how the code has been memoized. Now let's see how this has improved our time complexity. We know that since for each pair I and j, the function is called exactly once, and I will ask how many unique ordered pairs, how many unique pairs are there I and j. Okay, order is considered, that means 1 2 is different from 2 1. Okay, then I will say if there are n such indices and m such indices j, then there will be n cross m such unique pairs. So that is the time complexity, because I'm calling the function for n cross m times. Okay, so that's how the time complexity has reduced from being exponential to quadratic. Okay, so how this will this work for the constraints that we are given in the problem? Yes, because n and m goes up to 1000, and 1000 into 1000 is 10 raised to the power 6. That will give me a time 10 raised to the power 8, which is 0.01 seconds, which is within the time limit of 1 second, which is fixed for the most of the judges. So this will not give me TLE, but rather it will execute fine on the judge. Okay, so let's see so this was the memoized code, but we know that in dynamic programming we have two approaches of solving a problem. The second approach, the first approach is memoization, that is top-down approach, and the another approach is bottom-up manner. In bottom-up solution, we build the solution of larger problem, starting from using the solutions of the smaller problems. So this is how we are in this slide. We shall learn how to do that. So these are the strings, and this is the DP. This is the DP table, and I declare the DP table here. And what I'm doing here, I'm iterating over all the prefixes. So I start from A. So I use a pointer I. I start from the first character, I is pointing here, and I use another pointer j, which iterate over B, starting from the first character, and I try to match if the character number I and character j matches or not. If they match, then the result for that particular set of indices, that particular pair of indices dpij, it represents the longest common subsequence for the strings a and b. So for the prefix of string a from 0 to I, and for the prefix of string b from 0 to j. So that's what dpij is representing. Okay, so to find the result for LCS of these prefixes, I would have to know the result for the prefixes 0 to I-1, and for in case of B from 0 to j-1. Okay, so and that I have already stored in the dp array. So dpi-1 gives me that result, dpi-1 j-1 and since the characters are matching, I'm assuming the characters are matching, the character number I of the string A is matching with the character number J of the string B, then this result will be incremented by 1. So that's how I am covering this case. So it is covered here. So if the ith character is matching with jth character, I have to check for the longest common substring of the prefixes of lengths I minus 1 for A and J minus 1 for B. Okay, so that's the case here. And the last the final case, the last case that we have is if the characters at I and J does not match. In that case, we have to cover the two cases that we explained in the previous case. Either we take either we skip the character in string A. Here I'm skipping the character in string A, or I skip the character in string B and I take max of them. And this is the case where one of the strings is empty, or maybe both of the strings are empty. So in that case, I store 0. I simply store 0. So that means if I is 0, so this represents I, namely the string A, and this represents string B, namely the pointer J. And if I is 0, I am taking the, like I'm standing here, some hypothetical index of string A. In that case, for all the columns, I will put 0. Why? Because the LCS for a empty string versus a non-empty string or an empty string is always 0. And for this column, I will put 0 for all the rows, because the LCS for the empty string again is 0. Okay, because I'm standing here at some hypothetical index which do not have any character. So that's how I am initializing here in this case, and this case I've already explained. And for finding the result for dpij here, if this character is matching, let's say character number 2 of A is matching with the character number 2 of B, then I require the result here. Otherwise, I require results here and here. If the characters are not matching, I simply take max of these two results. Otherwise, I take this result and I add 1 to it and I store it here. So if the result here is C, then the result here will be C plus 1, in case these characters of the strings A and B are matching. Okay, so that's how, in this manner, I'm building the solution for the final strings. So final strings will be the entire string A and the entire string B. So this is of length 5 and this is of length 3. So this basically, okay, so this array has basically 5 rows, sorry for that. And here I will return the result dp and mn, where m is the length of this string A and b is the n is the length of string B. Okay, so that's all. That's the bottom up approach to build the solution for longest common subsequence problem. The time complexity for this solution is same as it was for the memoization, and the space complexity is also same, that is n cross m. So that's all for this video. Let me show you the code implementation for this. Okay, so this is the implementation of LCS in C++. So this is the base case. This is the case when nth and mth characters of strings A and B are matching. This is the case of memoization, and this is the case when the characters are not matching. This is the implementation in Java language, and this is the implementation in Python language. I have attached the solutions in the description. So thank you so much for watching this video, and stay tuned for more such content.